Actually, top tip, if I haven't given you this tip already, is it's often quite difficult to read a finished program in Agda and figure out, why the hell is it the way it is. A good tip, if you're trying to just make sense of something, is to comment it out and reconstruct it a little bit at a time, because then you can see what's in the Agda info buffer, and then you realize why the move was made. Yeah. So it's sad that kind of this sort of key clue to what's going on does not persist into the final document. But you can, at least, if you're actually at the controls, reconstruct it. Anyway, where did we get to? We got as far as the fact that we use an empty type to represent falsity, and that we have the joy of programming by saying, this can't be happening to me, get me out of here. So you don't, so you've got a choice when you're programming in Agda. You either have to deliver the output that is being asked of you, or if you can get out, you can solve your problem by refuting the input. So that's by way of saying, I don't have to get out of this situation because you can't really put me into this situation.
But there is a function solve the null type to any.
Yeah. I mean, well, that's it.
And it has a library name, which is bottom elimination.
Yes. It goes by various names. I like to call it magic. But anyhow, so we've looked at truth and conjunction. So the trivial thing, it was the empty record, and was represented by records of two things. So now we've looked at falsity, which is the data type with no choices. And next up is or, which is going to be a data type with two choices. So for each of these things, so the trivial thing, and that true is kind of like the neutral element that goes with and. So to say, X is true. To assert X and to assert X and true is their equivalent. So yeah, you can always glue on an extra component that's trivial. That's no bother. Likewise, you can always offer an extra choice that's impossible, and you haven't changed the situation. So false and or go together, true and go together. Not half. Anyway, so we're going to use, if we know what evidence for A consists of, and we know what evidence for B consists of, then we're going to say evidence for A or B is either evidence for A or evidence for B. So that's to say, if we play the game of how do you prove it and what good is it to know, right? How do you prove A or B? You pick one and you prove it. And that's kind of significant, because that you pick one under some circumstances amounts to supplying a bit of information. right? You announce 0 or 1. 0, I'm going to go left. 1, I'm going to go right. So there's information in a proof of A or B, whereas so far all of the connectives we've seen are essentially bureaucratic. There's no information in a proof of true. Yes. Yes. Yeah. So here's our data type. And it is, of course, made more complicated by paranoia about set theoretic levels, but that's eminently ignorable for the time being. And what we're basically saying is that, so this symbol is the symbol for disjoint union. And the disjoint bit is important. That's where the bit turns up. Disjoint union. So if you're going to prove A or B, then you give you choose a constructor, one of these two constructors, and there's your bit, that choice of constructor, so that these constructors, you can think of them as tags. They enable you to see clearly which of the two you've picked. And then if you choose injection 1, you have to deliver an A. If you pick injection 2, you have to deliver a B.
So that's enough to define it.
Yes.
You don't have to do both.
Yes. You don't have to worry about both of them. I mean, there might be situations where where both A and B have proofs, at which point you've got lots of options. You still have to pick one. So that's how you prove it. You pick one and you prove A or B by picking one of the two of them, by announcing which of the two you're going to prove and proving it. And what good is it to know? Well, if someone hands you a proof of A or B, you're allowed to reason by cases.
So we can pattern match on that proof.
Yes.
And we get our two cases, namely if A was injected. So we had a proof of A or we had a proof of B. And in both cases, we have to prove our goal.
All right. So that's...
The only thing A is with B is A or B.
Yeah. That's the whole point, yes. The person who made the proof supplied a bit of information saying which case you were in. And now we're looking at that bit and narrowing our problem down to two special cases. Well, it's got, I mean, we can, for products, for pairs, if you do case analysis, you get one case and you expose two pieces. Whereas here, we're exposing two cases. Yes. A bit of information has just turned up and we can make use of it. So here, if we're trying to prove A or B implies B or A, we just see which of the two we had, and now we know which way to turn.
So now we have a proof of A that we can inject on the right. So that's...
How do you type? Oh, is it backslash underscore and then digits give you tiny digits?
And here we are going to inject it on the left.
Yes.
And if we, for some reason, want superscript, we can do that with a caret and tiny digits. Well.
Okay. But yes. So apologies. Right. The action in this example is all in very tiny writing. Yes. My dictum of notation design is, if your action is all in the subscripts, punch yourself in the face and choose a better notation. But this message has not arrived here. There's also, of course, at least I'm glad the projections were also proj 1 and proj 2. It's one of these things where, depending on whether you encounter mathematicians or computer scientists, these things will be numbered 1 and 2, or they'll be numbered 0 and 1. And these fuckers have let the side down. Listen,
You mean the side.
This information, we're encoding a bit. And this bit is 1 or 2.
So does that mean there's, if you have function from A to something and function from B to something, you get a function from A to something by just injecting it and then going through on both cases?
Right. So again, it's only weak.
So, oh yeah, you said it.
Right. So there's which things are equal. We're heading that way. We also realize that equality has turned up in your coursework, so we had better make sure you know what's going on.
Before equality, let's maybe finish the classical connectives.
Yes.
And the only one left is negation. And what could be a proof of not A? That is to say that A is impossible, or if someone claims that they can give us a proof of A, something bad would happen, like something impossible. And we've already seen something that is impossible, namely providing a proof of the bottom type, of the empty type. So now we can model negation as a proof into the bottom type. So this is a function from A into the empty type. And this is also how we state our proposition. So now let's see how to prove something with that. And Agda would be very, very keen to use that shortcut that we defined, not. And if you actually want to see the definition of that, you can type Control-U, Control-U, Control-C, Control-dot. So this is a bit of mouthful, but any command, you can prepend it with Control-U, Control-U to ask Agda to full formalize the goal.
Yes, do more computation, look harder. I like to think of it as kind of swearing in Emacs.
Will it always be able to play more right?
Yes, it's like Control-C, Control-dot, or Control-C, Control-comma is what's going on. Control-U, Control-U, Control-C, Control-comma is what the fuck's going on.
So now if we type Control-U, Control-U, Control-C, Control-comma, we see that we are asked to produce a function into the bottom, but we have our argument. So whenever you see not A, think of, oh, here's your hypothetical A, please provide me a proof of the impossible.
Yeah.
So it can act always with the normalized.
Yeah.
Sorry, fully normalized.
Yes, it can.
So now we have that our function that can produce a value of the empty type, so we can just apply it. And the argument we should supply is the value of a unit type. And as we discuss it, we can be very lazy and just ask Agda to fill that for us, because we know that there is only one possible value. And Agda would be perfectly happy to do so.
Does it have another name? Is there a name that canonical name for it?
Yeah, that was
in the library. It's called TT.
Oh yeah.
So that was the canonical inhabitant of the unit type.
Cool.
Seems like a strange choice of name to me, but there we go. It's a relic from the 1970s, where people used to write the elements of the Boolean type as a bold T for true and a bold F for false, which they would render in ASCII as double T and double F. So this is 1970s for true. Anyhow, let's have a look at this one.
Yeah, so now we are actually in a very auspicious situation. So every time you end up with a proof of A and a proof of not A in your context, you can do a clever stuff and just get out and produce a value of any type. So let's see what happens. So let's first introduce the variables.
Actually, yeah. So that's also good typographical convention. You can see that this thing with no space between the not and the A is nothing special. It's just an identifier, but it's a suggestive one.
So is that not the function?
Yeah, yes. If there was a space, then this would be a strange invocation of a defined function on the left-hand side. It would be a syntax error. But there's no space. This is just some old identifier, but it's an identifier that has been chosen to be suggestive of its type.
And if we normalize its type, we see that it is a function into bottom. And if we remember from an example from last time, we had this function, what was it called? Example 6, that given a value into the empty type produces anything. Or that was the bottom elimination in the library. So we can just use that.
Okay, and now, yeah, so that's a kind of bold move. It's where you say, I'm not going to do what you want. I'm going to prove false instead. So yeah, and then our contradiction is exactly a function that proves false, and the input for that function. Excellent. Good to go.
So this could be a last resort escape mechanism, like you're stuck and, or maybe if I can somehow produce a proof of bottom, I can get away.
Yeah. So that invocation of x6 is a way of changing tack. It's a way of saying, okay, I'm giving up on producing this output. I'm going to refute the input instead, which we then do by manufacturing a contradiction.
This is implicitly saying every type has no, every type does that. Yeah.
Indeed. So that's cool. The other thing you can do is make use of with. So if you can produce a contradiction.
So again, with, we were using that on the left-hand side to in a way to go back in time to see, to give an expression and pattern match on it to see how it was constructed.
Yes, so there's bring to the left-hand side this extra useful thing. So yeah.
And that is the syntax, like you write your expression. So you have the function and the arguments, you write with, you write your expression, and then you omit the equality. And then on the next line, you can do this shortcut to say, oh, just copy the previous line, the line above. Then bar and introduce the variable that stands for the with expression. And now we can pattern match with that variable.
Yeah, look before you leap. Yes, you can see we've now acquired an X in the empty type by exploiting our contradiction. So if we pattern match on it, we get the empty parentheses of bullshit.
The not a after with is actually applying the function
yes.
a type that goes from a to the empty
yes.
with the term a.
Yes. So a proof of a is false is a way of saying, well, if you happen to have an a lying around, you're very lucky. So yeah.
So that was what we had in the context. So as a convention, every time you see not something in the homework, for example, that would be a function producing a value in the empty type.
Right.
And I think we're in a position to do more exciting stuff and talk about men being mortal and Socrates.
Yes. Yeah. Yes. So we've done the propositional stuff, the usual bits and pieces. We will come back if we've got time to why things are not quite what you might be used to, but now let's start using logic to talk about things.
So this is where truth tables can't happen.
Yeah, truth tables not our game. But yeah, so now we're going to start talking about how to use logic to talk about things. So the idea, we're going to work with predicates on sets. So if you've got some set A, what's a predicate on A? Well, you might think, hang on, it's a function from A to the Booleans. That's so something that tests elements. But no, that's not the way we play this game. We instead give a function from A into set. So instead of giving a computer program that computes a Boolean value, instead you say, what is the evidence that a particular value of type A has some property? So we're going to characterize. If we're talking about properties of things, we're going to say, what is it to be evidence for that property? So we're not just saying what's true, what's false. We're saying what constitutes evidence. And sometimes it looks pretty similar. So
it's not what's true or false, it's what's true or false and what can be proved to make
yes. What evidence would you accept? So here's an example. So you can, this is an ordinary function type. Okay, so you can see here we've got a set 1 showing up because the set 1 is the type of set. Remember, set is the type of boring ordinary things that don't talk about sets. And then set 1 is the type of types which talk about boring sets in general, but don't talk about things that talk about sets. Yeah, yes. So this it goes on forever. This is basically Bertrand Russell's escape from sort of paradoxes of self-reference, is to sort of slice the world up into things that don't talk about sets that don't talk about sets. Are at level 0, then if you talk about level 0 sets, you're in general, then you're at level 1, and so on. Yeah, so here's an example of just using ordinary programming to build a predicate. We're gonna check whether we're going to say, what's the evidence that a given number is even? And we do it by actually looking at the number. We say, well, if the number is 0, then I'm already happy, right? You don't need to work hard to convince me that 0 is even. That's trivial. And on the other hand, if the number is 1, then I'm going to make it really difficult for you to convince me that 1 is even by choosing to say, oh, falsity is the evidence that I would accept for the evenness of 1. And then if the number is at least 2, then you can convince me that your number is even by subtracting 2 and giving me the evidence that that number is even. So this is just a program.
And notice in the last clause, it is also, we're very convincing to Agda to allow us to write is even equals is even, but it is quite apparent that the argument we are applying it to is smaller on the right-hand side. So Agda is perfectly happy with that definition.
Yes, Agda's checking that And it's willing to notice. It gets as far as peeling off more than one constructor is is fine. When Agda is checking whether stuff is getting smaller, it doesn't, as long as it's smaller by at least one step, it's happy.
So is even right? That's a function.
That's a function, and we're going to make use of that function. We're going to make use of much more control U business. So you can see here, our goal was is even 4, but Agda is actually running that program. So 4 is Arabic notation for suck, 0. Thank goodness we were allowed to write Arabic notation. And yeah, if you just run that program, the program that we just wrote, but you don't have to run it because Agda will run it for you, then that will compute to the trivial goal. So we can prove it.
The type of is even 4 is just true.
Yeah. By straightforwardly just by running this program. So that's the thing. Agda will run the program as you've written it in the course of type checking. So that's a key power that we use when we write a program. It's not just a matter of, there's some runtime system that will run this program. The type checker will run the program, and it will run the program symbolically, right? If you have expressions with 3 variables, then we're good. Okay, so again, here in this one, if we want to refute that 5 is even, but that's pretty good news because our goal is not is even 5, but if we ask Agda to normalize the goal, turns out we're actually trying to prove false implies false, which is relatively straightforward. So yeah, you've got a choice here because you can either give back the proof of false that came in, or you can point out that it's false and refute the input. Either's fine.
Is even itself is a type, assuming that a number it becomes a type.
Yes, it's a.
Oh, you're getting something from
yes,
that.
it's a.
It's a function of that.
It's a function that computes types, and that's one of the nice things is that as far as we're concerned, types are first-class values, right? We can write programs that compute them. We can chuck them around.
So there's also a nice correspondence to logic. So if you have a predicate and you instantiate all its you supply individuals, you get a proposition. So this is also what's happening here.
Yeah.
We have a predicate on natural numbers. We give a natural number, and then we have plain old proposition the way we saw them last week on Tuesday.
Yeah, you have to be a little bit careful in this situation because sets are more interesting sometimes than what we're used to propositions being. So in particular, although we haven't here, we've been very careful to make sure that at the end of the day, we're computing the empty type or the unit type, which don't offer much variety. But you can imagine that there might be more than one way to give valid evidence for a proposition. And we might be able to tell those ways apart. So here, we're writing a function that computes a set. There's no, just from the type of is even, there's no guarantee that proofs of evenness are unique. We can see that the way we happen to have defined it ensures that proofs of evenness are unique. But choosing to represent evidence as things that live in sets means that if you want uniqueness, you have to think a little harder.
I assume you can have functions that it's W type from M to type 1, and that will be a proposition, predicate about type 1 things. Sorry, type things. Is there one the other way around if you have a function from M to just some random actual term? Is that sort of a 0th level of the predicates?
Well, we can write functions that compute values. It's harder to see. Well, okay. So what you would then end up doing is the sort of thing you can do, for example, is you can write a very important predicate on the Booleans. You can write the predicate that a given Boolean is the true value. And then if you have a function, so we could write the Boolean function that tests whether something is even. So we could write a function from nat to bool. Yeah. And then we could say, we could check that, we could form the proposition that something is even by demanding that that Boolean is true. So that's one way to shrink logic, is to say we're going to use ordinary values like truth values as proxies for sets of evidence. So this is a thing we actually often do.
So now maybe let's write a predicate.
Uh-huh.
And when is a thing strictly greater than 1? So what can we do in this situation? And we can pattern match and discard the cases when it's 0 and 1. So is 0 strictly greater than 1? No. Now we can pattern match again to get the case for 1. This is also negative. And now we're in a position to say that Higgs plus 2, or something that's at least 2, is always going to be greater than 1. So we can supply top here. And it's also easy to combine predicates. So now we have spelled out a predicate with the suggestive name less than 3.
I always think this symbol looks like a gust of wind.
Sorry for asking this. Could we refer to this as such n, the bottom line, and it just has x equals false for the top for everything below it?
Yeah, you can cut this down by. Agda does allow you to treat the equations as prioritized from top to bottom. So you could write this in 2 lines with the bottom line first, and then you could say essentially
everything else is
false otherwise. You have to be, so that sort of prioritization doesn't happen as a matter of course if you build left-hand sides by case splitting. Because case splitting will always, if you start out with your left-hand side being exhaustive and disjoint, and you refine it by case splitting, you'll preserve the property that your equations are exhaustive and disjoint. But humans can intervene.
This is a good property to have in general.
Yes, right, because when your left-hand sides are exhaustive and disjoint, as they are here, then you can believe all the equations.
You just
Agda will compute with the equations exactly as written. Yeah. Right. So here's an example. We want to show that 1 is less than 3 and 2 is greater than 1. And it turns out that that's a pair of trivial things because
So we
computation does the business.
Press Ctrl+C, Ctrl+R to introduce the single constructor and then fill in with the trivial value of the unit type.
Yeah. And indeed.
And we can even do a step further.
Yeah.
And put just that.
Yes.
Because then Agda can figure out, oh, this is.
Right. So this is the result of choosing records to represent. And true is that Agda will say, oh, I'm supposed to figure out a record. I'll figure out its individual components. And it does that repeatedly. Okay.
Okay.
Yeah. So as long as the types get smaller, right? So as long as you're not working with recursive records, which are a thing, but that's another story. Then the point is that the problem of figuring out what the value is gets smaller as you split the record up into components. So it's happy to keep doing it.
Now let's look at a very special predicate.
Yes, because you're going to need this thing, and we've transposed the definition. Okay, so is that \equiv? How do you type that? \con.
Or \2 times equals also.
Equals. That's nice. Okay, so this is Agda's definition of the type of evidence for being equal. The way we think about it is, you can see left of the colon, we've got some parameters that basically just say, pick anything in any type. So you choose some X in some type big A. And then, given that, we invent a predicate over things in A that amounts to being X. And then there's a constructor which says, as it happens, the only thing in A that you can give a proof for to say that it's X is X. Yeah, that's the thing that's X. So we're defining what is it to be X, which, when can you give evidence that a value of type A is X? Exactly when the value of type A is X. Now, there are various things we can worry about, and we will. This is not completely unproblematic as a way of talking about equality, not in the slightest. In fact, it's generally the case. Here's a piece of advice. If you're ever in a room full of type theorists and you want to start a fight, just bring up the idea of equality in casual conversation. It's the long-running war of how exactly to go about defining equality and how it should relate to stuff. And yeah, the other piece of advice I'd give is never trust a type theorist who hasn't changed their mind about equality at least once.
So is this equality here fully normalized?
Well, so we're going to get there. Okay, so, what we basically said here is that Agda will let you use the constructor refl, short for reflexivity, provided Agda can see why the things on both sides of the equal sign are the same. And remember, Agda tests those sorts of things. It's willing to do computation in order to do that. So what?
Is this the first time we see a constructor with a certain type?
We saw vectors, where the empty vector insisted on having a zero length, and cons insisted on having a non-zero length. And here we are insisting on something being x. So here, it's okay, right. That's rather the point. The point is that what we're saying is equality, as far as we're concerned, is whatever it is Agda can figure out. So if Agda can figure out by computation that two things are equal, then great. So that's good from one point of view, because guess what? It'll do the arithmetic, right? How do we prove that 5 plus 3 equals 8? We just say, over to you, Agda. Do some bloody work. Yes.
That equality is a refl definition. It's a different one from the function one, and it's a built-in Agda one.
Yes.
That's what we do.
Although it's, well, so what we're actually saying is that that 3 bar equals is rendering as a predicate exactly the same concept that 2 bar equals allows you to extend.
So they're
Yes.
3 bar equals at the top, right?
Yeah, so this is 3 bar equals, 3 bar equals, 3 bar equals. So that's making a notion of evidence. But what we're saying is we accept as equals things which compute to be equal. So here we get the good side of that, because Agda will compute that 5 plus 3 normalizes to 8. So proving 5 plus 3 equals 8 reduces to proving 8 equals 8. So we're good to proceed with our reflexivity constructor. This one we win. Okay. Now, you're in situations in your coursework where you're asked to prove some equations. So, okay, right. We're playing the usual game. How do you make friends with a type? You figure out how you build things in the type. We've just figured out, yes, you can use the reflexivity constructor once Agda can see why the two things are equal. Right. The thing that's essentially philosophically problematic with that is that computers are stupid. So if what we're saying is that Agda will accept things are equal if it can figure out why they're equal, that's going to be disappointing because it's a computer and it's stupid. Yeah. Here we're lucky, right? It'll do this much arithmetic, but yeah. So the problem with this notion of equalities is that it's a bit conservative. There's some things it's not going to do for us. And that it will be a source of frustration. Anyway, the other thing you do when you're making friends with a type is you ask, what use is it to be given an element of this type? So here we've been given a proof that x is 2. And we're trying to prove that x plus 4 is 6. So first of all, we should check that refl doesn't solve the problem. Right? What's going on here, right? Just trying to build models, right? You should understand that merely knowing an equation doesn't, knowing a 3-bar equals equation doesn't have any impact on the computation that Agda is willing to do. That hypothetical P doesn't change how Agda normalizes things in the slightest. That's just a random fact. There's nothing special about it in the slightest. So correspondingly, when we're trying to figure out, does REFL prove x plus 4 equals 6? We normalize both sides. The right-hand side, 6, is already a normal form. And the left-hand side, x plus 4, but plus is defined by recursion on its first argument in this instance. So x plus 4 is stuck because of that free variable, x. So this, I mean, if you normalize, if you do control U, control U, control C, control comma, you see, even when we normalize as much as possible, we are stuck. Agda cannot make these two things equal. So REFL isn't going to work. However, if we pattern match on our assumption, something cool happens. Agda is willing to go, which constructor was P made by? Well, there's only one constructor of the equality type, and that's reflexivity. But if P was made by reflexivity, then X must have been 2. So this is a classic example of looking at one piece of information in order to gain information about something else. We looked at P and we learned something about X. So it's kind of weird in dependently typed programming that you've got this, you can see things out the corner of your eye. We looked directly at P and saw it was REFL, but from that, we also learned more about X. So it really has substituted 2 for X in the goal as a result of checking that P really was REFL.
This next REFL we're about to find is a different REFL from the previous REFL.
Yes. This REFL is 2 equals 2. This REFL is 6 equals 6. So yes, you can see now this goal is going to compute, right? That goal becomes 6 equals 6.
Is that when you fully normalize it?
Yes. So now REFL works. So we did some extra case analysis. Okay, so that's one way. So this only works when one of the sides of the equal sign is a variable. There are some, which equations can you stare at? Generally speaking, it'll work for equations where one side is a variable, and it will do all sorts of stuff if you've got data type constructors on both sides of an equation. It will do that sort of simplification. So, well, you'll see what works and what doesn't. Okay, but there's another way to make use of equality. So another thing we can do here, there's a special trick. There's a keyword called rewrite. So you can say rewrite by, and you give some term which is a proof of an equation, in this case P. And what happens? What happens is that Agda goes looking for every occurrence of the left-hand side of the equation in the goal, and indeed even in the rest of the context. And it constructs a proof exploiting the fact that equality is substitutive. So it is, in fact, for this simple example, exactly the same. But you'll often find that, yes, okay, so what just happened, we gave it a proof of x equals 2 and it turned the x into 2. And now we're good to finish the goal in the same problem. So yeah, so in fact, this proof is this proof in disguise. But yeah, rewrites will work harder.
Maybe we can introduce another variable.
Yeah.
And see how that will affect our rewrite.
Yes, you might want to put an x plus y in the goal. Right. Now you might have a fun time if you're not careful about associativity. Yes. Let's get the brackets in the right place. Yeah, so
we can revolt.
Yeah, it's still happy. Whereas, let's show what happens if we try and do it by pattern matching instead.
So now we can try to pattern match on P.
And we go, yeah, I can't see why to make it reflexivity. Right, because this is not a problem. It can't. So when you do dependent pattern matching, when you do case analysis, it's willing to substitute for variables, but it's not willing to do any more advanced reasoning. So rewrite is doing something special. It's actually saying, look for the left-hand side of the equation and actually replace all occurrences of the left-hand side with a new variable.
Right.
Yeah, so what it's really doing is saying, actually, x plus y is now a thing of interest. I'm going to call it z, and I'm going to treat this as a proof that z equals 2. And I'm going to turn this x plus y into z as well. And now when I pattern match on my proof of z equals 2, z will be substituted by 2.
So is that the only difference?
So rewrite is doing the extra work to put in that abstraction.
So rewrite is a simple replace to a new variable.
Yes, that's the deal. Rewrite is abstract the left-hand side with a new variable, and then pattern match. Whereas this is just pattern match. So rewrite is working harder in general.
And we needed the rewrite on the left. We needed the P on the left-hand side. So you have P space rewrite space P. The rewrite P will be what turns P into 2. And the first P would be the statement that's.
Yeah, so this is our input. And then this is some proof of an equation. And in this case, it happens to be a proof that we received as an input. But it could be any old proof of an equation.
And I think we're almost running out of time, but maybe there's a few minutes for something that could be quite useful. And this is a lot of times you might end up in situations where you have an equality, but it is not as direct. So you would end up in a situation of a function applied to the left and right hand side of the equality, while also knowing that A equals B. So this happens quite frequently. You're proving something and you end up in a function that's applied on the both hand sides, since you want to peel that off and then continue with proving the simple equality. And let's see how we can write that function. So we have two sets, and we are given a function from A to B. And then we have if we have two inhabitants of A, and we know on evidence that they're equal, then we want to state that the function of
fx equals f1. And that needs to be 3 bar equal. That, yeah, that's a y.
Yes.
Yeah. You're speeding up and yeah, you can tell we're out of time.
Yes. So we have our function and we have our equality. So now what can we do here? Well, because this is a simple equality, we can pattern match on it.
Yes. Well, yeah. Once if you see a variable on one side, then you can definitely pattern match on it, and it'll substitute the variable. So here we're going to win.
And now we see that we can just put ref, because it's clear enough for Agda that this is.
Right. We should shut up. But yeah, we'll come back to this because this pattern matching on equations or using rewrite is only possible when you're still working at the left-hand side of a program. It's not possible when you're in the middle of building an expression on the right-hand side. Whereas once you have this thing as a library function, this is useful for building equations, building proofs of equations in all sorts of situations.
And I think it's a library function. It is called conc.
Yes, it's usually called Kong.
Short from concurrence. And if you ignore all the stuff that talks about levels, you can see it is the same function. So we have a type that is a set, and we have another type, our A and B. Then we have our function f and our equality.
Okay. So that's so. All right.
And you don't need the P there.
Uh, well, so Kong, well, this is a.
And the definition of Kong doesn't have the P, that's what I'm asking.
Yeah, Kong needs the P as in, it's just, all that's happening is that it takes the same information in the same order. So it's, yeah.
Yeah, but let's maybe leave our definition.